In this video, we'll be looking at the ARIMA model. When we combine differencing, which comes under integration, with autoregression and a moving average model, we obtain an ARIMA model. We'll look at differencing and integration later. ARIMA is an acronym for Autoregressive Integrated Moving Average. The Box-Jenkins methodology is a strategy or procedure that can be used to build an ARIMA model. The equation of the full model can be written as y dash t, that is equal to c plus summation of I equal to 1 to p alpha I y dash t minus I plus summation of I equal to 1 to q theta I epsilon t minus I plus epsilon t. ARIMA is made of three parts, namely AR, which is the autoregressive model, I, which is the integration, MA, which is the moving average model. AR is autoregressive model. In an autoregressive model, we forecast the variables of interest using a linear combination of past values of the same variable. Therefore, yt is equal to c plus summation of I equal to 1 to p phi I y t minus I plus epsilon t. We looked at the AR model in a previous video. I stands for integration. Differencing in statistics is a transformation applied to a non-stationary time series in order to make it stationary. To check if data is stationary or not, we use various tests like ADF test. To difference the data, the difference between consecutive observations is computed. Mathematically, this is shown as yt dash is equal to yt minus 1. We can use several other mathematical functions to achieve differentiation. When data becomes stationary after differencing, we do predictions on the difference data. We then do de-differencing on these predictions to obtain predictions for the original data.
George Box and Gwilym Jenkins were the first to propose integration, that is, differencing of non-stationary data to make it stationary. A lot of real-world data is not stationary, but for time series analysis, we need stationary data. Take a look at this sample data. After applying the ADF test, the p-value returned is 0.71, which is much greater than 0.05. Thus, this data is not stationary. We'll use the concept of differencing to make this data stationary and suitable for time series analysis. After applying the log function on our sample data, we get this new plot. The p-value after applying the ADF test is 0.21, which is still greater than 0.05. So we need further differencing. After the second step of differencing, we perform first order differencing, in which the value of the previous time step is subtracted from the value at the current time step. We get a new plot which has a p-value of 0.04 after applying the ADF test, which is much lesser than 0.05, which means that we have successfully differenced our data.
Next is MA, which is the moving average model. A moving average model uses past forecast errors rather than using past values of the forecast variable in a regression-like model. The equation for MA is yt is equal to c plus summation of I equal to 1 to q theta I epsilon t minus I plus epsilon t. We covered MA in a past video. ARIMA is defined by three variables, p, d and q. P is the number of lagged values we consider in the autoregressive part. The value of P is calculated from the PACF plot of the data. D is the number of times the data is differenced. Q is the number of error terms of the past time steps in the moving average part. The value of Q is calculated from the ACF plot of the data. Now that we have an understanding of the ARIMA model, we will use it to model a sample time series data. Real life data can be modeled in the same way.
Consider this: you have gotten a new internship role at a company. Your boss wants you to buy coffee for all the employees in the office each day. You don't want coffee to go waste, but you also need to buy enough coffee for everyone. Additionally, not everyone in the office will drink coffee every day. So each day, you will have to make predictions such that the amount of coffee you buy is equal to the required amount of coffee. Luckily, you find data that the previous intern maintained. This data contains information about the required amount of coffee, the predictions that the previous intern made for purchasing coffee, and the error in the required and predicted value. You find that this data is stationary. The errors look like white noise. So, you would like to model it with ARIMA. You plot the ACF and PACF plots for the required amount of coffee in the obtained data and obtain the following plots. From the PACF plot, we get to know that the value of P or the order of AR in ARIMA should be 2. From the ACF plot, we get to know that the value of Q or the order of MA in ARIMA should be 1. As the data was stationary, we need not apply differentiation, so the value of D is 0. Therefore, we can model the data as ARIMA 201 model. We use linear regression to find the equation for the ARIMA 201 model. The equation comes out as yt is equal to 1 plus 0.6 yt minus 1 plus 0.3 yt minus 2 plus 0.5 epsilon t minus 1. Here yt is the prediction for the current time step, yt minus 1 and yt minus 2 are the lagged values, and epsilon t minus 1 is the error term for the previous time step. The shown table contains data provided by the previous intern. Day 1 is the day before yesterday and day 2 is yesterday. So you have to make predictions from day 3 onwards. At the end of each day, you will get to know the actual coffee requirement for that day. The amount of coffee that you will purchase on day 3 is represented by Y3. You can calculate Y3 from the ARIMA equation. Therefore, Y3 is equal to 1 plus 0.6 into Y2 plus 0.3 into Y1 plus 0.5 into epsilon 2. Here, Y2 is the coffee that was required on day 2 and Y1 is the coffee that was required on day 1. Epsilon 2 is the error on day 2. Therefore, y3 is equal to 1 plus 0.6 into 12 plus 0.3 into 14 plus 0.5 into 0. Therefore, y3, that is the coffee that you will purchase on day 3, is equal to 12.4. For this example, we consider that the fractional values are also valid. At the end of day 3, your boss informs you that the actual coffee requirement was 14. Therefore, error on day 3 represented by epsilon 3 is equal to 14 minus 12.4, that is equal to 1.6. Coffee purchased on day 4 is represented by y4 and can be calculated using the ARIMA equation. Therefore, y4 is equal to 1 plus 0.6 into y3 plus 0.3 into y2 plus 0.5 into epsilon 3. Therefore, y4 is equal to 1 plus 0.6 into 14 plus 0.3 into 12 plus 0.5 into 1.6. Therefore, y4 is equal to 13.8. At the end of day 4, your boss informs you that the actual coffee requirement for that day was 13. Therefore, error on day 4, which is epsilon 4, is equal to 13 minus 13.8, that is equal to minus 0.8. Coffee purchased on day 5, which is y5, is equal to 1 plus 0.6 into y4 plus 0.3 into y3 plus 0.5 into epsilon 4. Therefore, y5 is equal to 1 plus 0.6 into 13 plus 0.3 into 14 plus 0.5 into minus 0.8. Therefore, y5 is equal to 12.6. At the end of day 5, your boss informs you that the coffee requirement for that day was 11. Therefore, error on day 5 is equal to epsilon 5 is equal to 11 minus 12.6, that is equal to minus 1.6. Coffee purchased on day 6 is equal to y6, that is equal to 1 plus 0.6 into y5 plus 0.3 into y4 plus 0.5 into epsilon 5. Therefore, y6 is equal to 1 plus 0.6 into 11 plus 0.3 into 13 plus 0.5 into minus 1.6. Therefore, y6 is equal to 10.7. The actual coffee requirement for day 6 was 10. Therefore, epsilon 6 is equal to 10 minus 10.7, that is equal to minus 0.7. Coffee purchased on day 7 is y7. y7 is equal to 1 plus 0.6 into y6 plus 0.3 into y5 plus 0.5 into epsilon 6. y7 is equal to 1 plus 0.6 into 10 plus 0.3 into 11 plus 0.5 into minus 0.7. Therefore, y7 is equal to 9.95. Actual requirement of coffee on day 7 was 11. Therefore, epsilon 7 is equal to 11 minus 9.95, which is equal to 1.05. If we plot our predicted values and the actual requirement of coffee, we see that there is a close fit between the prediction plot and the actual plot. So, ARIMA 201 is a good model for this time series data.
In this video, we looked at the ARIMA model In the next video, we will have a look at the Python implementation of ARIMA.